Okay, let's start. Good evening, everyone. I'm Shivani Thok, and I welcome you all for the week 5 tutorial for the course of Modern Digital Communication Techniques. And yeah, so let's start. So, as every time, I'll first start with the recap of week 5 content, and followed by I'll take few questions which are related to the content which was covered in this particular week. Okay, so let's start with this week 5 content. So this week started with continuing the low pass representation, low pass equivalent representation for systems, and we saw that if I have a system, let's say system HT, system India with impulse response H of t, and it is excited by an input RT, and its input is ST, and it has an output of RT. So this is a baseband thing. Sorry, not baseband, band pass system, and we saw that this SRST, this S of t is also band pass, this HT is also band pass, and we had seen how to represent this ST in its low pass equivalent, which was SLT, and or expressing this ST in terms of its low pass equivalent, which was simply real part of SLT into e power j 2 pi FCT. And similarly we had the similar representation for this HT. Now the next thing that we had to do was this representation of the output, low pass equivalent representation of this output RT. For that we had started by taking the Fourier transform of this band pass signal, which is RF, and we know that as this is an LTI system, linear and time invariant system, so this RT is simply convolution of this ST and HT, which means that in frequency domain, this R of f, the Fourier transform of this output RT will be simply R of f, which is multiplication of Fourier transform of this impulse response multiplied with Fourier transform of the signal. And after simplifying a lot, in terms of HL of t and SL of t, HL of f and SL of f comes out something like this. So if we compare with the standard equation of any band pass signal in terms of its low pass equivalent, we found that this term HL of, so we found that RL of f, RL of f is simply HL of f multiplied by SL of f, which means that this RL of t is simply convolution of SLT into HLT. After looking at this, the next thing that was discussed was representation of bandpass stationary process. So we started by considering the white sense stationary process. So what do you mean by a white sense stationary process? Its moments up to second order, that is mean, variance and correlation. All of these are independent of time instant. They just depend on the delay between the two time instances. So that is white sense stationary, and we started with a a band pass white sense stationary process, which can be represented in terms of an equivalent low pass equivalent signal, which is ZT, where this ZT is simply xt plus jyt, and after simplifying this nt, we get it something like this: xt into cos 2 pi fct, yt into sin 2 pi fct, which is exactly similar to the way we had represented any any band pass signal in the previous week. After that, so this thing is similar. This thing is general for all kind of all kind of band pass processes. Now, if this nt is WSS, that is, it is white sense stationary, then this phi excess of tau is equal to phi yy of tau. So what do you mean by phi excess of xx of tau? So this phi xx of tau is simply expectation of x of t into x of t plus tau, and this phi yy of tau is simply expectation of yt into y of t plus tau. So these two things are same. And next thing that is seen was something like this, which is phi xy of tau is equal to minus phi yx of tau. So this phi xy of tau is simply expectation of y of t into x of t plus tau. We'll see this, and xy is, okay, let me write it. Phi yx of tau is equal to expectation of xt into y of t plus tau. Okay. Since this derivation was little bit complicated, I'm going to take it as a question in upcoming, as one of the questions. So this will be much more clear there. Now this phi nn of tau, which is simply autocorrelation of this nt, comes out to be real part of phi zz tau into e power j 2 pi fct. This is also a similar representation as this, and this phi zz tau is simply phi xx tau plus j times phi yx tau. And another thing that was seen was this phi zz of tau is conjugate symmetric, which means that if I take its Fourier transform, it will be a real quantity. After looking at bandpass stationary processes, we went on to go for white noise, and we assumed that this white noise is a stationary process with a flat TST, that is, for all the frequency range its value is constant. And we also looked at the equivalent baseband representation of this, and this phi zzt came out something like this. And we said that as this B is very large, this tends to something like an impulse. After looking at these stochastic processes and representation of noise, the next thing that we went was looking at the vector and signal spaces. So what do you mean by a vector space? So it is a collection of vectors which satisfy some certain properties, which we won't be going into much detail, that you can find in any linear algebra course. So some of the operations or properties which are associated with any vector space that were discussed. So the first thing that was discussed was this inner product. So let me first say that v1 and v2 are two vectors, and these are, let's say, n dimension. That is, v1 is simply something like this: v11, v12, and so on till v1n. Okay, so this inner product is given as v1 dot v2, and this is simply summation I equal to 1 to n v1I into v2I. And if it is conjugate, then we'll put a conjugate sign here. So for now, let's consider a real thing. After that, orthogonal and orthonormal vectors are considered. So suppose I have a collection of vectors, let's say v1 till vm, then these are orthogonal if vi dot vj is equal to 0 for all I not equal to j. If this property holds true, if this property holds true, then these are orthogonal. And along with this orthogonality, if vi dot vi, which is written as norm vi square, if this is equal to 1, then together, if both of these properties are satisfied, then together this is known as orthonormal. Vector v2 is also a similar thing. Vector v2 is something like this: v21, v22, and so on till v2n. Okay. Yeah. So this is this thing here. This is orthogonality and orthonormality. Then the next thing that was discussed was this triangular inequality. So it says that if I take this, then this is less than or equal to norm of V2, norm of V1 plus norm of V2. This is triangular inequality. After that, the Cauchy-Schwarz inequality was introduced. So this Cauchy-Schwarz inequality says that if I take inner product of these two, that is V1 dot V2, and take a mod, this will be less than or equal to norm of V1 into norm of V2, and this holds with equality only when V1 is some constant times V2, that is this V1 is linear function of this V2. And after that, we looked at this Gram Schmidt procedure. So this Gram Schmidt procedure, if I have been given a set of vectors, so it allows us to construct a set of orthonormal vectors from the given set of vectors that we are having. So this, I'll take few examples of this Gram Schmidt procedure that will be more clear what exactly is happening there. I'll emphasize more at that point. After vector spaces, signal spaces were discussed, and it is very similar to vector spaces, and same properties hold with the signal space also. So for the signal space, this inner product is, directly go like this. This inner product is given as x1t comma x2t. This is simple notation, and this is nothing but integral from minus infinity to infinity x1t x2t dt. This is inner product. And if this says orthogonality, two signals are orthogonal if x1t comma x2t is equal to 0, it means that these two signals are orthogonal. And along with that, if magnitude of norm of x1t is equal to 1 and norm of x2t is equal to 1, then these are orthonormal as well. Similar to vectors, we have triangular inequality here as well. So the triangular inequality here says that if I take norm of x1t plus x2t, then this is less than or equal to norm of x1t plus norm of x2t. And what do you mean by norm here? So norm of any signal xt is simply inner product of xt with itself raised to the power 1 by 2, that is square root of it. After that, we have this Cauchy-Schwarz inequality. So it says that if I consider magnitude of x1t comma x2t, then this is less than or equal to norm of x1t multiplied by norm of x2t, and equality if and only if x1t is some alpha times x2t. And again, similar to this vector spaces, we had considered Gram Schmidt procedure. I won't say much about this Gram Schmidt orthogonalization procedure right now. We'll solve some questions on this for both vectors and signal spaces. That will be much clearer at that point. Let me see if there are any questions. Okay. I'll encourage you to please unmute your mic and then ask questions. Actually, it's very difficult to look at chat continuously. But yeah, orthogonal property and orthonormal property, just wait for some time. I have some questions on it. Some questions. So it will be very clear when you solve those questions. Just wait. But I'll still repeat it once, that see, this is the inner product that we are having. If I have two vectors v1 and v2, and if their inner product is equal to 0, then they are known as orthogonal vectors. It's only this much. Yeah, we'll see one example for this orthogonality. Okay, so after that, after doing this, the digital modulation was started, and for digital modulation it was said that it maps k bits to one waveform. So basically after encoder we have this modulator block. So an input to this modulator block, so if I have this modulator, and input to this is basically a bit stream. So what it does is, it will group k bits, and then map each of this k bit to one waveform. For example, if k is equal to, let's say, 2, so if k is equal to 2, there will be 4 possibilities of grouping. So each of this has to be mapped to a unique waveform. So these are unique or distinct waveforms, which means that there should be m equal to 2 to the power k possible distinct waveforms, and these waveforms are transmitted for fixed duration. So it was mentioned in the lecture that what differentiates the analog and digital modulation techniques is, I after looking at the group of bits I have to choose one of these waveform by looking at these bits. That is, after grouping, if I have the bit stream or those two bits as 0 0, I will choose s1t. If it is 0 1, then I'll choose s2t. Like that, I have to make a choice of a waveform, and that waveform is transmitted for a fixed duration. However, this is not the case in analog modulation. For analog modulation, for entire duration, you are modulating that message signal over your carrier, either through your amplitude or phase or your frequency in any one of this. However, here we have a choice of this waveform, like looking at those bits which are given to you by that digital interface, that encoder is giving you a bit stream. So that, looking at this bit stream, I'll make a choice of the waveform that I'll need to send, and each of this bit is coming at a particular duration. With a particular duration, it is generated at a particular rate. It is taking some particular duration to get generated. So each of this group will also have some time duration. So I'll transmit this signal only for that particular time duration. So basically, for a fixed duration, I'll be sending that particular waveform. I hope it is clear. And then classification for modulation schemes was discussed, which was based on this memory. So based on memory, we have either memoryless modulation techniques or with memory modulation techniques. So basically, when I have memoryless modulation technique, it has nothing to do whatever I have transmitted previously or whatever I'm going to transmit in future. However, if it is based on memory, it will look at the past values which I am going to transmit. So currently we'll focus on memoryless, and we'll have one or two examples for with memory based modulation schemes. After that, it was based on linearity. So for linearity, basically it says that this modulation scheme should satisfy so this modulation scheme should satisfy my linearity property. So how it is linear, how it is non-linear, all these things will be covered in upcoming lectures. as we have just started with this pulse amplitude modulation, which is um, one of the linear modulation scheme. So in upcoming weeks, we'll see why it is linear and why it is what exactly it is, why it is memoryless, and all those things we'll discuss. So basically, this pulse amplitude modulation, or PAM, is given by this waveform SMT. So corresponding to bits, we have these signals, right? S1, S2, S3 till SM. We have this SMT, which is given by real part of AMGT into e power j 2 pi FCT. This AM is the amplitude level which we are selecting, and it is generally given by 2m minus 1 minus m whole multiplied by d, where this d is the distance between two consecutive points. So basically what is happening is, this is your axis, this is 0, this is d, let's say d by 2, this is 3d by 2, and so on, and this is minus d by 2, this is minus 3d by 2, and so on. So now this distance between any two adjacent points is basically equal to d. So this is what we are saying here, that this is the distance between two adjacent amplitude levels. And this GT is pulse shaping waveform. Again, what is the use of this pulse shaping waveform? All these things will be discussed in upcoming lectures. So just wait for what is going to happen. And this waveform we are transmitting for time ranging from 0 to t, where this t is given by k times tb, and this tb is basically my bit duration. This is bit duration. What do we mean by bit duration? We have this bit stream coming from my my encoder. So each of this bit is generated for tb durations, or rather takes time as tb duration. From where this tb come? So we have this, before this encoding process is happening, we have an analog signal, we sample it, we quantize it, we have some sampling frequency. After that sampling, due to that sampling frequency, in each second we have some particular number of samples coming up, and each of that sample is quantized to some particular discrete level, which is then encoded to bits. So now we have so due to the sampling frequency and number of samples generated in a particular second, we have a particular time allocated, or a particular time required for generation of this particular bit, and that is known as this bit duration. So this was just introduced to us, pulse amplitude modulation. We'll look over it in more detail in upcoming lectures that are in week 6. Any questions regarding the content of this week? If there are no questions, I'll go ahead and with solving. Okay. So if there are no questions, I'll just go ahead and take questions. So as we can look here, in this week we had major concepts of this stationary processes, then vector and signal spaces, and introduction to this modulation scheme. This modulation schemes, there are not many questions which can be covered. So in this week, I'll cover the questions which are related to the signal spaces, vector spaces, that is Gram Schmidt, and also I'll look at the stationary processes, like how to find autocorrelation and those kind of things. So let's start with a simple question. So what does this question say? Determine the autocorrelation function of the stochastic process, which is given by this xt equal to a sine 2 pi fct plus theta, where this theta is uniformly distributed from 0 to 2 pi, and this fc is constant. Is this process a wide sense stationary process? Okay. Now, before going ahead, let me first say what does this mean. This theta is uniformly distributed over 0 to 2 pi. What does this mean? Theta is uniform random variable which takes values in 0 to 2 pi, and it is a continuous random variable. So this has its own distribution, which we can distribution, or let's say it has its own PDF and CDF. So the PDF of this is given as 1 over 2 pi for theta belonging to 0 to 2 pi, and it is 0 otherwise. Okay. Yeah, so what do we need to find is, we have this stochastic process here. We have this stochastic process xt is equal to a sine 2 pi fct plus theta, and it is said that this a is constant and this fc is constant. These both are constant, and this theta is random variable. Therefore, this autocorrelation is basically phi xx of tau, or let's not denote it right now. Let's say this is given by expectation of xt x of t plus tau. So this is the quantity that we need to find. This is the quantity that we need to find. Okay, so let's start here. Now again, this expectation is with respect to which variable? This expectation has to be with respect to a random variable. So now, what is the random variable here? It is theta. So this expectation is with respect to theta. Okay, so let's try to do it. And in general, how do we find expectation of it? So let us first look at how to find expectation. So if x is a random variable, with PDF fx of x, then expectation of x is integral from minus infinity to infinity, or yeah, let's say, okay, minus infinity to infinity x fx x dx. And if g of x is a function of random variable x, then expectation of g of x is given as integral from minus infinity to infinity g of x fx of x dx. Now if we look carefully here, this is your expectation xt into x of t plus tau, and this expectation is with respect to this variable theta, this random variable theta, and this xt is a function of theta, which means that this xt into x of t plus tau is a function of theta, means it is a function of this random variable theta. So how will we find this expectation? So similar to this equation which I have mentioned here. Yes, this one. Just let me know once you are done. Okay, thanks. Okay, so now what do we need to find is this expectation of xt into xt plus tau, right? Which is a function of theta. So basically this is g of theta. So similar to this definition which I have written here, expectation of x of t into x of t plus tau will be simply integral f of theta theta into x of t plus tau d theta. So now this f of theta is basically this 1 over 2 pi for range 0 to 2 pi, otherwise it is 0. So this integral here, I can just take it from 0 to 2 pi. For all other values it will be 0. So for 0 to 2 pi, this f of theta theta is simply 1 upon 2 pi, which is constant, so I can just take it outside. From 0 to 2 pi, this xt is a sine 2 pi fct plus theta, and this x of t plus tau is a sine 2 pi fct plus tau plus theta d theta. So this I can simply write as 1 upon 2 pi integral 0 to 2 pi, this a square is constant, I can take it outside, sine 2 pi fct plus theta into sine 2 pi fct plus 2 pi fc tau plus theta d theta. So this is basically similar to sine A, sine B, and sine A sine B is nothing but 1 by 2 cos of A minus B minus cos of A plus B. So if we do that, what do we have here? A is 2 pi fct plus theta minus this quantity sine 2 pi fct plus 2 pi fc tau plus theta. So if I subtract this and this, so what I am left with is simply this quantity here. So this is equal to a square upon 2 pi integral from 0 to 2 pi cos of 2 pi fct theta fct plus theta minus sine 2 pi fct plus 2 pi fc tau plus theta. So that results in minus 2 pi fc tau, but cos of minus something is again cos of that particular thing. So this is simply 2 pi fc tau minus what do we have here? So that will be simply addition of these two quantities. So this 2 pi fct just gets added. So what we have is sine of 4 pi fct plus 2 pi fc tau plus theta d theta, and this whole thing is divided by 2. Okay, so I'll just take this quantity on the next page. So this is what we are having. So I can write this as a square upon 4 pi integral 0 to 2 pi. This is also okay, let me write it. Cos 2 pi fc tau d theta minus a square upon 4 pi integral 0 to do one thing. Now it will be okay. Oh, sorry, it's cos, not sine. Yeah. So this is cos of 4 pi fct plus 2 pi fc tau plus theta d theta. So now this thing is independent of theta. So this can come out and this thing will be simply, this first thing will be simply a square upon 4 pi cos 2 pi fc tau theta from 0 to 2 pi, and minus this thing will be a square upon 4 pi minus sine 4 pi fct plus 2 pi fc tau. Why am I writing minus? Yeah, sine 2 pi fct plus 2 pi fc tau plus theta, and this is from 0 to 2 pi. Now this thing here is square upon 4 pi cos 2 pi fc tau. This thing is simply 2 pi. So this is basically a square upon 4 pi into 2 pi minus a square upon 4 pi. Inside the bracket it is sine of some quantity. This some quantity plus 2 pi. So sine of anything plus 2 pi is that quantity itself. So I can write it as, okay, let me write it completely. Sine 4 pi fct plus 2 pi fc tau plus 2 pi minus sine 4 pi fct plus 2 pi fc tau. Now this thing here is simply equal to sine 4 pi fct plus 2 pi fc tau, because sine of, see this integration, how cos 2 pi fc, oh, it's there, it won't vanish, it will be there. Yeah, okay, so this is sine 4 pi fct. This term and this term are same. Also this term and this term are identically same. So this entire second term goes to 0. So what are we left with? We are left with simply a square upon 2 into cos of 2 pi fc tau. So now I can just write it as fxx of tau, and this is simply expectation of xt into x of t plus tau. Another thing, if we look at expectation, let me add, so this is the autocorrelation which we have found, and the next thing that is asked to us is whether it is a WSS process. So now let us find expectation of x of t. So that will be simply integral from 0 to 2 pi f of theta theta into xt d theta, and this comes out to be 0 to 2 pi. F of this quantity is simply 1 over 2 pi, and xt is a sine 2 pi fct plus theta d theta, and this thing is equal to a upon 2 pi. Inside the bracket it is cos of minus cos of 2 pi fct plus theta from 0 to 2 pi. So this is a upon 2 pi, let's say a minus sign here. So this is cos of 2 pi fct plus 2 pi minus cos of 2 pi fct Now again cos of anything plus 2 pi, so this quantity is again equal to cos of 2 pi fct, so this goes to 0. This term, this entire term goes to 0. So now this is basically equal to 0. Now if you observe carefully, your expectation is 0. We have expectation of xt as 0, and we have expectation of xt plus tau is equal to a square by 2 cos 2 pi fc tau. This is basically your second moment, or let's say correlation, and this is your expectation of xt. So if you look at both of these are function of tau only and don't depend on t, and hence these are WSS. Any questions here? A stochastic process, you can say that at every time instant I am having a random variable. It is some sort of a time varying, it is a function which varies with time, and its amplitude is a, like at every time instant it acts as a random variable. Like if you observe here, this is a function of time, x of t, it is a function of time. It is a function of time, and it is a theta which is uniformly distributed from 0 to 2 pi. So for every time instant there will be one realization of this theta, so it will be a random quantity. Is it clear? Yeah. Just look at a random a probability course or a random processes course, you will get a better idea of what it is. Okay, so let's start with the second question. So what it says is, let Z of t be a WSS process if xt and yt are real and imaginary parts of low pass equivalent of zt, then show that phi xs of tau is equal to phi yy of tau, and phi xy of tau is minus phi yx of tau. This thing was derived in class, but still I like to redo this because it's these are a bit, the derivation is a bit complex one, like it involves a lot of calculations, so I'll just do it once so that it is understood. This function, autocorrelation function, this autocorrelation function, if it is independent of time, it doesn't depend on your time, it just depends on how much delay you are there you have. So if that is the case, then in that situation it is a WSS process. Yeah, it's not this xt, this autocorrelation function, it is expectation of xt into x of t plus tau. This xt will depend on time. It is a time dependent function. Okay. So let's start with this. So what it's given is zt is a WSS process and xt and yt are real and imaginary parts of the low pass equivalent of zt, which means that this zt, this is band pass, and this let ZL of t be its equivalent low pass, and it is nothing but xt plus j times yt. So as discussed previously, this zt I can write as xt cos of 2 pi fct minus yt sine of 2 pi fct. Now it is said that this zt is WSS process, which means that since zt is yes, I am assuming that it is a band pass. I am mentioning here that these are real and imaginary parts of the low pass equivalent of zt. So I am considering it to be a band pass assumption. Yeah. So this phi zz of tau, this should be only a function of tau since it is WSS. Okay, so let's try to find this phi zz of tau. So this is expectation of zt into zt plus tau. This is zt into zt plus tau. So this is equal to expectation of this zt is xt cos 2 pi fct minus yt sine 2 pi fct multiplied by xt plus tau cos 2 pi fc t plus tau minus yt plus tau into sine 2 pi fc t plus tau Okay, this is what we need to find. So this I can write as, so this is equal to expectation of, after multiplying the terms, it is xt into xt plus tau cos 2 pi fct into cos 2 pi fc t plus tau minus, you can separate out these, minus expectation of xt into yt plus tau cos 2 pi fct into sine 2 pi fc t plus tau minus expectation of yt into xt plus tau sine 2 pi fct into cos of 2 pi fc t plus tau plus expectation of yt into yt plus tau sine of 2 pi fct into sine of 2 pi fc t plus tau. Okay. Now if we observe carefully, the only random variable here are these x and y, and not these sine and cos. These are not random. These quantities are not random. So I just need to take, these can come out of the expectation, so that this is simply this. This is also simply this. Similarly, these two are like this. Okay, and this quantity here, is simply pi xx of tau. This quantity here is phi yx of tau. This quantity here is phi xy of tau. So this is the same definition which we had looked previously. Here, phi xy of tau is phi yt into x of t plus tau. Xy of tau. Same thing we are using here. Okay, and this thing here is simply phi yy of tau. So what we are having is phi xx of tau multiplied by this thing. This thing here is like cos A cos B. So again, so this cos A cos B.
Yeah.
Hello?
Yeah.
Hello, please unmute yourself. If you have a doubt, please. Yeah, thanks. So this is like cos A cos B. We have cos A cos B as cos A minus B plus cos of A plus B. Okay, so this comes out to be cos A minus cos of A minus B. This is my A and this is my B. So the first term that comes out to be is phi xx, and this whole thing divided by 2. Yeah. So the first term here comes out to be cos of A minus B, that is 2 pi fct minus 2 pi fct plus tau. So this is simply 2 pi fc tau plus cos of 4 pi fct plus 2 pi fc tau divided by 2. The second term here is minus phi yx of tau, and this is cos A, or this is something like sin A cos B. So this is simply sine of A plus B plus sine of A minus B by 2. Here A is this quantity, that is 2 pi fct plus tau, and B is 2 pi fct. So sine A plus B will be simply sine of 2 pi 4 pi fct plus 2 pi fc tau plus sine of 2 pi fc tau divided by 2. The third thing is also same. So this is simply minus phi xy of tau. Here a is 2 pi fct and b is 2 pi fct plus tau. So what we are having here is sine a plus b is same term, that is sine of 4 pi fct plus 2 pi fc tau, and then it will be minus sine 2 pi fc tau. The fourth term that we are having here is phi y of tau, and this gets multiplied by, this is sin a sin b, and we have seen this previously that this is cos a minus b minus cos a plus b by 2. So this is cos a minus b, so this will be cos of 2 pi fc tau minus cos of 4 pi fct plus 2 pi fc tau divided by 2. This is also divided by 2. So now let us look at the terms which are corresponding to cos 2 pi fc tau, and let's combine these two. Okay. So what we have is, we have phi xx of tau plus phi yy of tau divided by 2 into cos 2 pi fc tau. Then let us look at the terms which are corresponding to these quantities. Cos 4 pi fc tau like this. So let's look at this. So what do we have is phi xx of tau minus phi yy of tau whole divided by 2 multiplied by cos of 4 pi fct plus 2 pi fc tau. So this is basically corresponding to these, and this is basically corresponding to cos 2 pi fc tau. Then let us look at the terms corresponding to sin 2 pi fc tau. So what do we have here is plus, it is minus phi yx tau plus phi xy tau by 2 into sin 2 pi fc tau. So this is corresponding to this term, and let us take the remaining term, which is this. So what we have here is plus minus phi yx tau minus phi xy of tau divided by 2 multiplied by sin 4 pi fct plus 2 pi fc tau. So this is corresponding to these terms. Okay. Now we mentioned that this is basically a Whiteson stationary function, which means this phi zz of tau should only be a function of t, should only be a function of tau. However, whatever we are getting here is function of t and tau as well. Like this is a function of t and tau, this is also a function of t and tau. Now these two quantities are not zero. So in order to have this entire expression as only a function of tau, this term should go to 0 and this term should go to 0. When will these two terms go to 0? These two terms will go to 0 only when, since z of t is WSS, this function above equation should depend only on tau and not on t, which means that phi xx of tau should be equal to phi yy of tau If this is true, then this term here will go to 0, and phi yx of tau should be equal to minus phi xy of tau. If that is the case, then this term will go to 0. Is it clear? Okay, if there are no questions, then I'll go for the next question that I have to take. So this is the third and last question, which is related to stochastic processes. So it is said that this NT is a zero mean stationary narrowband process. The autocorrelation function of this equivalent low pass representation ZT is equal to XT plus JYT is given as X Z conjugate T into ZT plus tau. We need to show that this expectation ZT into ZT plus tau is so this we need to show that this is equal to 0. Yeah, we need to show that this expectation is equal to 0, and after that we need to find this second the value of these expectations which are mentioned here. So we have given that this NT is stationary, which means that it is WSS as well. It is stationary, which means that it will be stationary by sense also. Okay, so if this is stationary, then this fxx of tau will be equal to fyy of tau, and fxy of tau will be equal to minus fyx of tau. Okay, so if that is the case, then let us look at what is this. Let us look at expectation of zt into z of t plus tau. So this is equal to expectation of zt is simply xt plus j times yt, and zt plus tau is x of t plus tau plus j times y of t plus tau. So this comes out to be expectation xt plus tau plus j times expectation xt yt plus tau plus expectation j times expectation yt xt plus tau plus expectation yt plus tau. Okay, so this is what we are having. So let me write it again. Expectation zt plus tau is expectation xt plus tau plus expectation yt. Sorry, this is not plus, this will be minus. It will be j into j, so that will be minus. So minus expectation yt into yt plus tau plus j times expectation xt yt plus tau plus expectation xt plus tau into yt. Okay, so this is simply phi xx of tau minus phi yy of tau plus j times phi xy of tau plus phi yx of tau. Okay, so now since it is WSS, this phi xx of tau is equal to phi yy of tau, which means that this is equal to 0. Similarly, phi xy of tau is equal to minus times phi yx of tau. So this is also equal to 0. So This means that this is equal to 0, and this is what we wanted to prove. So we proved that expectation zt into zt plus tau is equal to 0. Now let us see what we need to look at next. So what is being asked is, we have been asked to solve these two things, and we have been given this autocorrelation function. Rz of tau is n naught delta tau, and v is given as integration from 0 to t zt, and we need to find this expectation v square and expectation magnitude v square. Okay, so now let us do it. So let us solve this thing. Okay, so let us first solve expectation v square. So this is basically expectation of integral of zt, integral of t zt whole square, which I can write as expectation, this is dt, which I can write as expectation 0 to t zt1 dt1 multiplied by 0 to t zt2 dt2. This is equal to expectation integral from 0 to t, integral from 0 to t zt1 zt2 dt1 dt2, and this is equal to integral from 0 to t, integral from 0 to t. Expectation is a linear operator, so expectation of integration is basically integration of expectations. So this expectation I can take inside. So this is zt1 zt2 dt1 dt2. Now if we observe, so suppose this is t1, we have this t1 and this t2, I can write it as t1 plus tau. So this entire term which is available here is simply expectation of zt1 into zt1 plus tau, right? And in the previous part we proved that expectation of zt into zt plus tau is simply equal to 0 for all values of tau and all values of t, and therefore this expectation itself is equal to 0, and hence what we were finding was expectation v square, this is equal to 0. I hope this part is clear, and if this is clear, now let us try to solve. So now we'll solve the second part. So we'll consider, yeah, so now let us consider expectation magnitude v square, and this is basically equal to expectation of v into v conjugate. So this I can write as expectation integral 0 to t zt1 dt1 multiplied by integral 0 to t z conjugate t1, sorry, z conjugate t2 into dt2. So again this I can write as expectation of integral from 0 to t, integral from 0 to t zt1 into z conjugate of t2 dt1 dt2, and this is basically, again I can take out these integrations and take expectation inside. So this is expectation of zt1 to z conjugate of t2 dt1 dt2, right? Now this again I can write this t2 as, or let's say I can write this t1 as t2 plus tau, and here tau is nothing but t1 minus t2, right? Now if we go above, if we look at the question here, we have been given that this rz of tau is n naught delta tau, and this rz of tau is simply this quantity here, expectation of z conjugate t into z t plus tau. So here our t plus tau is basically t1 and t is t2. So this is what we are having here. We have expectation of z t2 plus tau into z conjugate of t2. So this should be this quantity here. This quantity here should be basically equal to delta, or to be more specific, it should be n naught delta tau, and however this tau is t1 minus t2, so this I can write as n naught delta t1 minus t2. So this is equal to integral from 0 to t n naught delta t1 minus t2 dt1 dt2. This I can take out this n naught, so this n naught is simply a constant, I can take it out. And this t1 and t2 both are ranging from let's say 0 to t. T1 and T2 both are ranging from 0 to t, which means that this T1 minus T2 will be in the similar range. So this thing is simply n naught 0 to t, and integration of an impulse in that range will be simply equal to 1 in dt2, and this is true if T1 minus T2 is in 0 to t, otherwise it will be equal to 0. If this and this will be equal to 0 if T1 minus T2 does not belong to 0 to t. So let's consider this case only. So this will be equal to n naught t. I hope this is clear. Okay, if there are no further doubts, then let's go ahead for the next question. So the next question that I have here is, we need to show that the columns and rows of this following matrix are orthonormal. So what we are having here is, let's say this is C1, this is C2, and C3. This is R1, this is R2, this is R3, and we need to show Ri, Rj equal to 0 and norm of Ri equal to 1 for all I not equal to j. Similarly, we need to show that Ci dot Cj is equal to 0 and norm of Ci is equal to 1. This is what we need to show. So let us first consider R1 dot R2. So what does this R1 dot R2 mean? We need to do element by element multiplication, this into this and plus this into this plus this into this. So what we are having here is simply R1 dot R2 is equal to cos theta into sin theta. So this will be cos theta into sin theta. So this is equal to cos theta into sin theta plus minus sin theta into cos theta. So this will be equal to minus sin theta into cos theta, and then it will be 0 into 0, which is 0, and these first two terms get cancelled, so this is simply equal to 0. Okay. Similarly, if I consider R1 dot R3, then I'll have to do element by element multiplication and then add the components of this r1 and r3. So this is basically cos theta into 0, which is 0, minus sine theta into 0, which is again 0, and this is 0 into 1, which is again 0. Similarly, if I go for r2 dot r3, again I need to do element by element multiplication of these and add them. So we have sine theta into 0 plus cos theta into 0 plus 0 into 1. So again this is equal to 0. Now let us look at what is r1 square. So if this is 1, then its square should also be equal to 1. So it is equivalent to show that if its square is equal to 1, then it is orthonormal. Okay, so till this point we are able to say that this is orthogonal because all of the dot products are 0. Now let us consider norm of r1 square. So norm of r1 square is basically square of this quantity plus square of this quantity plus square of this quantity. So this is basically equal to cos square theta plus minus sine square theta plus 0, and cos square theta plus sine square theta is simply equal to 1. Similarly, norm r2 square is sine square theta plus cos square theta, which is 1, plus 0. So this is also equal to cos square theta plus sine square theta, and this is equal to 1, and norm of r3 squared is equal to 0 plus 0 plus 1 square. So this is simply equal to 1. Since this condition is being satisfied, that is these dot products are 0, along with that the norms of these 3 rows are also 1, which means that rows are orthonormal. Now let us look at the columns. So let us see C1 dot C2. Now I need to do element by element multiplication of C1 and C2 and add them. That is, I need to look at cos theta into minus sine theta. So what we have is cos theta into minus sine theta plus sine theta into cos theta plus 0 into 0, that is 0. So this comes out to be 0. Then we have C1 dot C3. So this is equal to cos theta into 0, which is 0, sine theta into 0, which is again 0, plus 0 into 0, which is again 0. So this comes out to be 0. Then we have C2 into C3. So this is equal to minus sine theta into 0, which is 0, plus cos theta into 0, which is again 0, and this is 0 into 1, which is again 0. So this comes out to be 0. So again, since all the dot products are 0, we are assured that this particular set, that is C1, C2, C3, are a set of orthogonal vectors. Now let us consider the norms. So let us look at norm of C1 square. So norm of C1 square is cos square theta plus sine square theta plus 0. So this is equal to cos square theta plus sine square theta plus 0, which is equal to 1. Similarly, this C2 square is equal to minus sine square theta plus cos square theta plus 0, which is sine square theta plus cos square theta plus 0 is equal to 1, and norm of C3 squared is simply 0 plus 0 plus 1. So this is also equal to 1, and therefore we can say, since the dot products are 0 and all the norms are 1, the columns are orthonormal. Any questions? Okay, let's go for the next question then. This is the fifth question. So it says that we need to find the orthonormal basis corresponding to these vectors, which are 1 0 1, 1 1 0 and 2 1 0. So this will do by Gram Schmidt orthogonalization. Okay, so what do we have here? Let's say we need to find E1 hat, and this is basically will be equal to A1 upon norm of A1, A upon norm of A. Okay, so this is the first vector that we have to consider. This is Gram Schmidt procedure. So now this norm of A is simply under root of 1 square plus 2 square plus 1 square plus 0 square plus 1 square. So this is 1 square plus 0 square plus 1 square. So this is equal to under root 2. Therefore E1 hat is simply 101 divided by root 2, which comes out to be 1 by root 2, 0, 1 by root 2. This is the first vector that we are getting through Gram Schmidt procedure. So this is first vector. Now let us go for second. So for constructing second, what we need to do is we need to consider this vector and remove the components of this first vector which are along the direction of this vector. Okay, so how to do that? For that we'll project this vector over this and remove its component. Okay, so for that basically what we need to do is we need to remove the component of this from this, which means we'll have to project A on B and remove its component. Okay, so how do we do that? So that we do by constructing, first we'll construct an intermediate vector. So let's say it is E2 tilde, and this E2 tilde is given by B minus dot product of B and E1 hat multiplied by E1 hat. Okay, so now let us do this. Let us find B dot E1 hat. So that is equal to, let me write those vectors. So this is 1 0 1 dot product with 1 by root 2, 0, 1 by root 2, and this is simply element by element multiplication and adding. So this is 1 into 1 by root 2. This is 1 0 0, sorry, yeah, 1 into 1 by root 2, 0 into 0 and 0 into 0. So this is simply 1 by root 2. Therefore E2 tilde is basically B bar minus 1 by root 2 into E1 hat, which is equal to B is 101 minus 1 by root 2 into 1 by root 2, B is 100 0, 1 by root 2, which is equal to 100 minus 1 by 2, 0, 1 by 2, and this comes out to be 1 minus 1 by 2 is 1 by 2, 0 minus 1 by 2. So this is E2 hat. So is it actually are E1 hat and E2 hat orthogonal? Oh sorry, this is E1 tilde, and now we need to consider E2, and this E2 tilde is basically, sorry, we need to consider E2 hat. So this E2 hat is basically E2 tilde upon norm of E2 tilde, and norm of E2 tilde is simply under root of 1 by 4 plus 0 plus 1 by 4, So this is equal to under root of 1 by 2, which I can simply write as 1 by root 2. Okay, so now what I have here, this norm of is 1 by root 2, so this thing is 1 by root 2, so I can write it as root 2 into e2 tilde, which is equal to root 2 multiplied by 1 by root 2, 0 minus 1 by root 2, sorry, 1 by 2, 0 minus 1 by 2, and this comes out to be 1 by root 2, 0 minus 1 by root 2. So are these two orthogonal? So simple check we can do this. This will be 1 by root 2 into 1 by root 2, which is 1 by 2, and 1 by root 2 into minus 1 by root 2 will be minus 2. So this will be basically the dot product of e1 hat and e2 hat will be basically 1 by 2 plus 0 and minus 1 by 2. So yes, e1 hat and e2 hat are orthogonal. So like these you can go for quick checks that will allow you to check whether you are doing things correctly or not. And this is the second vector which we have, and now we'll look at the third one. So let us say it is e3 tilde, and e3 tilde will be, we need to subtract the components of a and b from c, that is we need to subtract the, or in other words we need to subtract the components along e1 hat and e2 hat from this c. Okay, so this will be basically c minus, this will be c minus yeah, dot product of c with e1 hat multiplied by e1 hat minus dot product of c with e2 hat into e2 hat. So this c into e1 hat is basically equal to, this c is 210 dot product with e1 hat, which is 1 by root 2, 0, 1 by root 2. So this comes out to be 2 by root 2, which is equal to root 2. And similarly, c into e2 hat is simply 210 dot product with 1 by root 2, 0 minus 1 by root 2, which is again 2 multiplied by 1 by root 2 plus 1 into 0 plus 0 into minus 1 by root 2. So this is also 2 by root 2, which is equal to root 2. So this e3 tilde is equal to, what is c? c is 210 minus root 2 times 1 by root 2, 0, 1 by root 2 minus root 2 times 1 by root 2, 0 minus 1 by root 2. So this is equal to 210 minus 101 minus 10 minus 1. So this comes out to be 2 minus 1 minus 1, which is 0, 1 minus 0 minus 0, so this is 1, and 0, 1 minus 0 minus 1 plus 1, again it is 0. So this is e3 tilde, and norm of e3 tilde is simply equal to 1. Therefore, e3 hat is 0, 1, 0. So the orthonormal set which we have obtained is basically 1 by root 2, 0, 1 by root 2, 1 by root 2, 0, minus 1 by root 2, and 0 1 0. I hope this is clear. If there are any questions, you may ask me. Okay, we'll see similar examples, more such examples. So again, we'll do this Gram Schmidt procedure. Okay. Yeah. So now we have this A, B and C vectors given here, and we need to find again the orthonormal set of vectors. So let us start with the first vector. So let's say this E1 tilde is A and E2 E1 hat is simply E1 tilde upon norm A, which is E1 tilde upon norm of E1 tilde, and norm of E1 tilde is simply under root of 0 plus 0 plus 1 square, which is equal to 1. Therefore, E1 hat is equal to 0 0 1. Okay, so this is E1 hat. Now let us find what is E2 hat. So for that, let us consider an intermediate vector, which is E2 tilde. So this will be B1 B minus B dot E1 hat multiplied by E1 hat. So this B dot E1 hat is equal to 0 0 1 dot product with 0 1 1, and this is equal to 0 plus 0 plus 1, which is equal to 1. Therefore, this E2 tilde will be B, that is 0 1 1 minus 1 into E1, that is 0 0 1, and this comes out to be 0 1 0. Now again, this E2 tilde norm, so norm of this E2 tilde is basically equal to under root of 0 plus 1 plus 0, which is equal to 1. Therefore, this E2 hat, which is simply E2 tilde upon norm of E2 tilde, is equal to E2 tilde, which comes out to be 0 1 0. Okay, now in similar fashion, let us consider the third basis. So this is E3 tilde. This will be equal to C minus C dot E1 hat into E1 hat minus C dot E2 hat into E2 hat. Okay, so now let us look at C dot E1 hat. So this is equal to 1 1 1. This C1 is 1 1 1. So this is equal to 1 1 1 multiplied by E1. This E1 is simply 0 0 1. So this is 0 0 1. So this is 0 plus 1 into 0 0 plus 1 into 1 1. So this is equal to 1. Similarly, if I have C1 into E2 hat, so this will be equal to C2, and this E2 is simply 0 1 0. So this is 0 plus 1 into 1 1 plus 1 into 0 0, which comes out to be 1. Therefore, this E3 tilde is C1, that is 1 1 1 minus 1 into E1. So this E1 is simply 0 0 1 minus 1 into minus 1 into this E2, which is 0 1 0, and this comes out to be 1 0 0. Therefore, orthogonal set, or to be very specific, it is orthonormal set of vectors is 0 0 1, 0 1 0 and 1 0 0. Now this is a very peculiar example of any basis. So this is like you can construct a vector x y z as x into 1 0 0 plus y into 0 1 0 plus z into 0 0 1 for all x y z in whichever space you are real or complex. So this is a very peculiar basis, and this is a basis always. This is always a basis, and therefore such a basis is known as, this set is known as standard basis of a vector space with whose dimension is 3, that is 3 element vector space. Just for, it was just for a just a side information. Yeah, again, will this Gram Schmidt takes time to understand, so it should be repeated multiple times. So this is the last question on Gram Schmidt for vectors. We'll take a small question on, what do we say, signals as well. Okay, signal spaces. So this is the last question on vectors. After this, I'll take the examples for signals. Okay, so again, what we are having here is 3 vectors, and we need to construct an orthonormal set of vectors using this. Okay, so let us start. So let us go with e1 hat, which is the first vector, which will be a upon norm of a, which is equal to 1 1 0 into 1 upon under root of 1 plus 1 plus 0. So this quantity is 1 by root 2. So this comes out to be 1 by root 2, 1 by root 2 and 0. So this is even hat. Now for second vector, we'll consider intermediate thing. So this will be b minus b dot even hat into even hat. So this b dot even hat is equal to 1 0 1 dot product with 1 1 by root 2, 1 by root 2, 0. Okay, when I'm writing this dot product, this means that this is a dot product, inner product. This is inner product. And this is equal to 1 by root 2 plus 0 plus 0. That is 1 into 1 by root 2 plus 0 into 1 by root 2 plus 1 into 0. So this is 1 by root 2. Okay. So therefore, e2 tilde is 1, this b, minus 1 by root 2, 1 by root 2, 1 by root 2, 0. So this is equal to 1 0 1 minus 1 by 2, 1 by 2, 0. So this comes out to be 1 minus 1 by 2, that is 1 by 2. 0 minus 1 by 2, so it is minus 1 by 2, and 1 minus 0 is 1. Now let us look at e2 tilde norm of this. So this is simply 1 by 4 plus 1 by 4 plus 1. So this comes out to be under root of 6 by 4, that is root 3 by 2. Okay. Yeah. Or let me write it as root 6 by 2. Yeah. Okay. So therefore E2 hat is simply E2 tilde upon norm of E2 tilde. So this will be equal to 2 by root 6 multiplied by 1 by 2 minus 1 by 2 and 1. So this comes out to be 1 by root 6 minus 1 by root 6 and 2 by root 6. This is E2 hat. That is our second orthonormal vector. And next we need to find the third one, that is E3 tilde. Let's start with that intermediate vector. So this E3 tilde will be C minus C inner product with E1 hat into E1 hat minus C inner product of E2 hat into E2 hat. So the C inner product with E1 hat is equal to, this C is simply 0, 1, 1 and dot product with 1 by root 2, 1 by root 2, 1 by root 2, sorry, 0. So this comes out to be 1 by root 2, and then it is C dot E2 hat. This is again 0, 1, 1 dot product with 1 by root 6 minus 1 by root 6, 2 by root 6. So this is minus 1 by root 6 plus 2 by root 6, which comes out to be 1 by root 6. Therefore this E3 tilde will be C, which is 0, 1, 1 minus 1 by root 2 into 1 by vector 1 by root 2, 1 by root 2, 0 minus 1 by root 6 multiplied by 1 by root 6 minus 1 by root 6 and 2 by root 6. So this is equal to 0, 1, 1 minus 1 by 2, 1 by 2, 0 minus 1 by 6 minus 1 by 6, 2 by 6. And this comes out to be minus 4 by 6, 4 by 6, 4 by 6, which I can write as 4 by 6 into minus 1, 1, 1, and therefore norm of E3 tilde will be 4 by 6 into under root of 1 square plus 1 square plus 1 square, which is equal to 4 by 6 root 3. Therefore this E3 hat, which is equal to E3 tilde upon norm of E3 tilde, this comes out to be 1 upon 4 by 6 root 3 multiplied by minus 1, 1, 1, which comes out to be minus 1 by root 3, 1 by root 3 and 1 by root 3. Therefore the set of orthonormal vectors which we have obtained is 1 by root 2, 1 by root 2, 0, then it is 1 by root 6 minus 1 by root 6 and 2 by root 6, and the last one is minus 1 by root 3, 1 by root 3 and 1 by root 3. I hope this is clear and there are no doubts. If there are any doubts, please let me know. Okay, if there are no doubts, then let's go ahead and look at the 8th question. So what does it say? It asks whether are the following signals orthogonal. So what do we need to check is we need to see is the inner product x1t and x2t is equal to 0. Okay, so let's start with the first one, that is, let us look at x1t into x2t, which is simply integration from minus infinity to infinity x1t x2t dt. This I can write as integral from minus infinity to infinity sine 2 pi fct into cos of 2 pi fct now dt, and this I can write as limit t tends to infinity integral from minus t by 2 to t by 2 sine of, this is I can multiply and divide by 2, so 2 sine 2 pi fct into cos 2 pi fct will be basically equal to sine of 4 pi fct by 2, and this is basically limit t tends to infinity 1 by 2 outside minus cos 4 pi fct upon 4 pi fc from, this will be from minus t by 2 to t by 2. So let me take this, okay, it will go fine. Let me adjust it in this page itself. Okay, yeah, and this thing is equal to minus 1 by 2 limit t tending to infinity, this is cos of 4 pi fct by 2 minus cos of 4 pi fc minus t by 2 or minus 4 pi fc t by 2, so this is also equal to 4 pi fc t by 2, which is equal to 0, which means that x1t and x2t are orthogonal. Is it clear? Okay, so now let us look at the second part of the same question. So it says that x1t, so it says that x1t is sine 2 pi fct, x2 is cos 2 pi fct, but now we are restricting that signal for a range of 0 to t. So this inner product x1t comma x2t is simply equal to, now instead of 0 to minus infinity to infinity, it will be from 0 to t sine 2 pi fct into cos of 2 pi fct dt, which again I can write as 1 by 2 integral 0 to t sine of 4 pi fct dt. This is equal to minus 1 by 2 cos of 4 pi fct divided by 4 pi fc from 0 to t, and this comes out to be minus 1 by 2 cos of 4 pi fct minus cos of 0, which is 1, multiplied by 1 upon 4 pi fc, and we have been given that this t is some integer multiple of fc, that is, from here I can say that TFC is K and this K is in integer. So I can write this quantity which is here as equal to K. So now this becomes 1 upon 8 pi FC 1 minus cos of K 4 pi. So basically it is integer multiple of 4 pi, or we can say that integer it is an integer multiple of 4 pi, and this is also equal to 1. So which means that this is equal to 0. And since this is equal to 0, these are orthogonal. Now one thing to note is this is orthogonal just because we are considering t is equal to k by fc. If this condition is not satisfied, then this thing here will not be equal to 1, and then those won't be orthogonal. And therefore in order to have these orthogonal, I need to keep this t as k by fc. Just because of this condition, I am getting it to be orthogonal. I hope this point is clear, and let's go to the next question, which is something like this. So again it is asking, are the following waveforms orthonormal? That is, we need to check, is inner product of fi of t, okay, we need to check inner product of fi comma fj, is it equal to 0 if I not equal to j, and 1 if I equal to j. Okay, so now here we are having three waveforms, and note that these are real signals. So fi comma inner product of fi comma fj will be equal to inner product of fj comma fi. So it suffices to just check one of the combinations, that is f1 inner product of f1t and f2t will be same as inner product of f2t and f1t here. Okay, so let's do that. So let us first check inner product of f1t comma in and f2t, and this is equal to integral f1t f2t dt. In general it is from minus infinity to infinity. Here the signal, all these three signals are ranging from 0 to 4. All are ranging from 0 to 4. So I can put these limits as 0 to 4. Now if you observe carefully, this f2t takes a constant value from 0 to 4, which is equal to 0.5. However, this f1t takes 0.5 for 0 to 2 and minus 0.5 for 2 to minus 4. So we can simply break these integrals into two parts. So it will be 0 to 2, f1t is 0.5 and f2t is again 0.5 dt, and plus it is 2 to 4, f1t is minus 0.5 and f2t is 0.5 dt. This comes out to be 0.5, this is 0.25. Integral 0 to 2 dt will be simply 2 minus 0, which is 2, minus 0.25 into 2, which is equal to 0. Let us check integral f1t and f3t. So now this, see here, this ft3 is changing its nature after every one interval. So basically we'll have to split this integral into 4 parts. So basically this will be equal to 0 to 1. Here in 0 to 1, f1t is 0.5 and f3t is also 0.5. So this is 0.5 dt, plus from 1 to 2, f1t is again 0.5. However, this f3t is minus 0.5 dt, plus 2 to 3. This is minus 0.5 and f3t is 0.5. So now it is minus 0.5 into 0.5 dt plus integral from 3 to 4 f1t is minus 0.5 and f3t is also minus 0.5, so it will be simply 0.5 into 0.5 dt. So the first term here comes out to be 0.25 into integral 0 to 1, so that is simply 1, minus 0.25 integral 1 to 2 dt, which is again 1, plus in minus 0.25 integral 2 to 3 dt, again 1, plus 0.25 integral 3 to 4, which is again 1. So this is again 0. Okay. Now let us consider the third one, that is integral f2t into f3t. Okay. So now again this f2t is constant as 0.5 for entire range of 0 to 4. However, this ft3 is again oscillating as like this. Okay. So this again will have to split into 4 integrals, so it will be 0 to 1. Here f2t is always 0.5, however ft3 is changing its value, so for f2t it is 0.5 and for this particular value f3t is 0.5, so again it will be multiplied by 0.5 dt plus integral 1 to 2 f2t is 0.5. However, now here f3t is minus 0.5, so ft3 is minus 0.5 dt plus integral 2 to 3 f2t is 0.5 and integral and ft3 is 0.5 dt plus integral 3 to 4 0.5 multiplied by minus 0.5. f3t is minus 0.5 here. Okay, so now the first integral is 0.25 into integral 0 to 1, which is 1, minus 0.25 into integral 1 to 2 dt, again 1, plus 0.25 integral 2 to 3 dt, which is 1, minus 0.25, which is again equal to 0. Okay, so from 1, 2 and 3, f1 of t, f2 of t and f3 of t, these are orthogonal. Now let us check if these are orthonormal. So for that we need to consider f1 of t square. See if norm of f1, okay, yeah, f1 of t square. So this is simply equal to integral 0 to t, 0 to 4 f1t square dt, which is equal to f1t is 0.5, f1t square will be 0.5 squared for entire range, right? So this I can write as 0 to 4 0.5 square, which is 0.25 integral 0 to 4 dt, which comes out to be 0.25 multiplied by 4, which is equal to 1. Similarly, if we consider f2t square, this thing is also 0.5 for entire range, so again this will be integral 0 to 4 0.5 square dt, which is simply 1. Similarly, if I go for ft3 square, so this is also 0.5 square for all the range, so this is simply 0 to 4 0.5 square dt, which is equal to again 1, which means that f1t, f2t and f3t are orthonormal. Okay, I hope this is clear. Please stop me if you have any doubts. If there are no doubts, then let us look at the next question that we are having here. So what do we need to do? We need to determine the set of orthonormal functions for the following four signals. So similar to our vector case, we'll be using Gram Schmidt procedure. Okay, so let's start. So for that, what we'll do is we'll consider intermediate. So let's start with first. We are having four signals, so we'll have four, at most four signals, four set of orthonormal functions. Okay, so let's start with the intermediate functions. So this f1 tilde t is simply s1t, and f hat t, f1 hat t is simply f1 tilde t upon e1, and this e1 is basically, sorry, under root e1. It is e1 is simply energy in this f1 hat t, so that will be simply integral 0 to 3 f1 hat t square dt. Here f1 tilde is simply s1, so therefore this will be 0 to 3, this is 2 square dt, which is 4 into integral 0 to 3 dt, which comes out to be 4 into 3, which is 12. Therefore f1 hat of t is simply s1 of t divided by root 12. Okay, so how will it look? Let us try to plot it. How will that thing look? It will look something like this. This is my t axis. This is 1, this is 2, this is 3, and this s1 is getting scaled by 1 by root 12, so that will be 2 by root 12, which is 2 upon 2 root 3, which is 1 by root 3. Okay, so this will be 1 by root 3, and this is my f1 hat of t, and this 1 by root 3 is basically 2 by root 12, and this is the first vector in our case. Okay, now let us consider the second vector. Let us consider second vector. So let me draw that second vector here. So this is 1, 2, 3, this is time axis. Let's say this is s2t, and this s2t is taking a value as 2 from 0 to 1. So this is 2 from 0 to 1. Okay, and the intermediate signal f2 tilde of t, this is equal to s2t minus s2t, inner product of s2t with f1 hat of t into f1 hat of t. Okay, so now we need to, let me draw this also. This is t, 1, 2, 3, and this is 1 by root 3, and this is simply f1 hat of t. This is what we are having. So now we need to find inner product f1 hat of t with s2t, and this will be equal to, this s2t is non-zero only for a range of 0 to 1. See, we need to multiply, we need to point-wise multiply these two signals. So this is non-zero only for a range of 0 to 1. So it will just be like this, that is 2 into, this is not 1 by root 2, this is 1 by root 3. 2 into 1 by root 3 dt, which comes out to be 2 by root 3. And so now what we need to do is, we have f2 tilde t is equal to s2t minus 2 by root 3 into f hat of t. So let us draw, this is t. So what we need to draw is, we'll draw here 2 by root 3 into f1 hat of t. So if I have 2 by root 3, it will be just every element will be multiplied by 2 by root 3. So this will be 2 by 3, like this. This is 2 by 3. Okay. And now what we need to find is this signal. So now let us draw here. Yeah. What we need to draw now is this is t, and this thing will be f2 tilde of t, which is s2 of t minus 2 by root 3 f1 hat of t. Okay, so we need to do element by element subtraction. So for this region, it will be 2 minus 2 by 3. So 2 minus 2 by 3 is simply 4 by 3. So in this region, this signal will be, so this is 4 by 3, and in this region, let me highlight this also. Yeah, and in this region, it will be 0 minus 2 by 3, that is minus 2 by 3. Yeah. So this is minus 2 by 3, and this is my, this signal here is my f2 tilde of t, and what I need to find is f2 hat of t. So this f2 hat of t is simply f2 tilde t upon e2 root e2, where e2 is integral from 0 to 3 f2 tilde t square dt, which is equal to integral from 0 to 1 4 by 3 square dt plus integral from 1 to 3 4 by 2 by 3 square dt. So this comes out to be 4 by 3 square plus 2 by 3 square into 2, and this comes out to be 8 by 3. Therefore f2 hat t is equal to f2 tilde t divided by under root 8 by 3. So this is basically root 3 upon 2 root 2. Okay, so now we need to find how this signal will look. That is, we'll need to multiply this f2 tilde t by the scaling factor which is here. Okay, so let me do that. This is t. Okay, this is my, this will be f3 f2 hat of t, and this for 1 2 3, this is 0. Yeah, so for 0 to 1, again I'll highlight these ranges, 0 to 1, and this is 1 to 2. For 0 to 1, my magnitude will be root 3 upon 2 root 2 multiplied by 4 by 3. So this is under root 2 by 3. So this will be under root 2 by 3, and from 1 to 3 it will be root 3 upon 2 root 2 multiplied by minus 2 by 3. So this comes out to be 1 by root 6. So this is minus 1 by root 6. Okay, and this is the third orthonormal vector that we are, second orthonormal vector that we are having. So this is the second one. Now what we need to do is we need to repeat the same thing for the third one. Okay, so now the next thing that we need to do is for the third one, yeah, so let's say f3 tilde t is the intermediate thing that we are having. So this will be s3t minus inner product of s3t with f1 hat of t into f1 hat of t minus inner product of s3t comma f2 hat of t into f2 hat of t. Okay, now this is how my s3t looks. So let me draw it again. So let me create a big thing here. Okay, yeah. So this is time axis. This is 1 2 3, and let me draw it above. One, two, three, and this S3T is basically minus 2. This is minus 2, and this is S3T. And let's draw here S1 F1 hat of T. This F1 hat of T is simply like this. So this is 1 by root 3 for all the values, that is 1, 2 and 3. Similarly, let us draw f2 hat of t, and f2 hat of t is something like this. So it is 2 by root 6, 2 by root under root of 2 by 3 here, and minus root 1 by 6 here. So this is under root 2 by 3, and this is minus 1 by root 6 here. That is, this is 1, 2 and 3. Yeah, okay. So now let us find this. Inner product of S3T and F1 hat of T. Okay, so now this will be only valid in this range, that is 1 to 3. So this will be 1 integration from 1 to 3. Here S3T is minus 2 and F1 hat of T is 1 by root 3. So this is minus 2 by root 3 into 2. So this comes out to be minus 4 by root 3. Similarly, let us do S3T, inner product of S3T with F2 hat of T, and this comes out to be integral from 1 to 3. Again this is minus 2 in this range, and this is minus 1 by root 6 dt. So this is 2 by root 6 into 2, which is equal to 4 by root 6. Okay, so now what we are having here is F3 tilde T is equal to S3T minus 4 by root 3 F1 hat of T minus, okay, let me write it properly, minus 4 by root 3 into F1 hat of T minus 4 by root 6 into F2 hat of T. So now let us draw these. This is 1, 2, 3. This is 1, 2, 3. So here what I am drawing, here I am sketching minus 4 by root 6 F1 hat of T. So if I minus 4 by root 3 F1 hat of T so now if I do this, this is basically minus 4 by root 6 multiplied by this quantity 1 by root 3. So that is basically minus 4 by 3. So this is like this, minus 4 by 3. This is time, and let me take this down. Yeah, and this is what I am plotting. This is 4 by root 6 F2 hat of T. And how does this look? So I'll need to multiply under root 2 by 3 into 4 by root 6. So that comes out to be 4 by 3. So this part here is 4 by 3, and minus 1 by root 6 multiplied by 4 by root 6. So this comes out to be minus 2 by 3. Okay. So now what we need to construct here at last is this T, and this is simply F3 tilde of T, and F3 tilde of T will be basically subtraction of this quantity, this signal, like we'll have to subtract this and this from this S3T. So let us look point by point. So this is 0, this is minus 4 by root 3, and this is again 4 by root 3. So it is 0, minus 4 by root 3 plus 4 by root 3. So in this range from 0 to 1, 1, 2, 3, in this range this is 0. Now let us look at the range from this. Let us look at this range. That is, let us look at 1 to 3, 1 to 3, and 1 to 3. So how is this looking? So this is basically minus 2. This is minus 2 plus 4 by root 3 plus 2 by root 3. So it is this at here, it is minus 2 plus 4 by root 3 plus 2 by root 3, which is again equal to 0. So therefore f3 tilde t is equal to 0 for all t, which implies that f3 hat of t is also 0 for all t. Is it clear? Okay, now we are left with the last thing that we need to do, and that is, okay, let me add a page. Yeah, and now we need to look at the fourth thing, that is f4 tilde of t. That is the fourth basis that we need to look at. So this intermediate thing, that is f4 tilde of 3, is simply s4 of t minus inner product of s4 of t multiplied by f1 t minus inner product of s4 of t multiplied by f2 t, and this is hat, f1 hat of t and f2 hat of t, and we won't be having third thing because this f3 hat of t is basically 0. Okay, so again for our convenience, let me just draw these. Okay, so let me draw s4 of t first. This is t 1 2 3, and s4 of t looks like this. It is 2 from 1 to 2. So this is s4 of t. s4 of t is 2. This is 2 from 1 to 2. Yeah. Okay, and then we have this t 1 2 3, and I'll plot f1 hat of t here, which is 1 by root 3. This is 1 by root 3 for all t, and then I'll draw f2 hat of t. This is 2 by root 2 by, this is under root 2 by 3 for this range, and minus 1 by root 6 for this range. So this is basically 1 2 3. Okay, so now let us find this thing, that is inner product of s4t with f1 hat of t, and this comes out to be integral. Now again, this s4 of t is just non-zero in this range, so this integral will be again from 0 to 2 into 1 by root 3 dt, which is equal to 2 by root 3 into 2, which comes out to be 4 by root 3. Okay, now similarly, let us find integration of inner product of s4t with f2 hat of t, and this is again, it will be non-zero from this range. However, this f2 hat of t changes from these two, like it is this here, positive here and some negative value here. So this I can write as integral 0 to 1 2 into under root 2 by 3 dt minus integral 1 to 2 1 by root 6 into 2. So this is basically 2 into 2 by under root of 2 by 3 minus 2 by root 6, and this 2 by root 6 is basically, I can write it as under root of 2 by 3, and this comes out to be under root of 2 by 3, and therefore s4 sorry f4 tilde t comes out to be s4 of t minus 4 by root 3 f1 hat of t minus under root of 2 by 3 into f2 hat of t. Okay, so now let us draw So now let us first draw under root 2 by 4 by root 3 into f1 hat of t. Now this f1 hat of t takes 1 by root 3 value. So this will be 1 by root 3 into 4 by root 3, which is simply 4 by 3. So this thing here is 4 by 3 for all the values of t from 0 to 3. Okay. Now next thing that we'll plot will be under root 2 by 3 into f2 hat of t. Okay, so now this f2 hat of t is 2 by under root of 2 by 3 for first. Okay, this just note, be careful that this is entirely under the root, huh? Yeah, so this is basically 2 by root 3 into 2 by root 3. So sorry, under root of 2 by 3 into under root of 2 by 3. So for this range, that is from 0 to 1, this will be 2 by root 3. I'm sorry, to under root of 2 by 3 into under root of 2 by 3, that will be 2 by 3. And for this range, that is 1 to 3, it will be 2 by root 3 into minus 1 by root 6. So it is under root of 2 by 3 into 1 by root 6. This is equal to under root 2 into 1 upon 3 into 6, which is simply equal to 1 by 3. Okay, so this is simply minus 1 by 3. And now let us draw f4 tilde t, and this f4 tilde t is basically s4 will be basically we'll have to subtract this and this from this. Okay, so let us look here. Let us look at the range from 1 to 2, like this range. So in this range, the signal that will be here, let me write it, 1 2 3, the signal that will be available here in this range, it will be 2 minus 4 by 3 minus 2 by 3. So this comes out to be 0. Okay, then let us look at this range from 1 to 2, from 1 to 2, from 1 to 2. So in this range, this will be 2 minus 4 by 3 plus 1 by 3. So this will be basically 2 minus 5 by 3, and this is basically equal to, wait, what did I do? Yeah, this is 2 minus 4 by 3. So this comes out to be equal to 1. Okay, so this is basically 2 minus 3 by 3, which is equal to 1. So this thing here is equal to 1. And now let us look at this range. This is this range, and now we'll look at the last range, which is here. here and here. So here this will be basically 0 minus 4 by 3 plus 1 by 3, which is equal to minus 1. So here we have minus 1. So this is how my F4 tilde t will be looking. Okay, and we know that F4 hat of t is simply F4 tilde t upon E4 under root of E4, and this E4 is simply integral from 0 to 3 F4 tilde t square dt. Now this is non-zero from 1 to 3 and the square of it will be 1 dt. So this comes out to be 2. So therefore F4 hat of t is simply F4 tilde t upon root 2. So what we are having, okay, so this is t, this is F4 hat of t 1, 2, 3, and this is simply getting multiplied by root 2. So here it will be 0, here it will be 1 by root 2, and here it will be minus 1 by root 2. So this is 1 by root 2 and this is minus 1 by root 2. Okay, and this is the fourth basis that we are having. So if we observe carefully this thing here, let me draw it again just for clarity. So the basis orthonormal basis that we have obtained are something like this. Okay, so this is first one, second, this is the fourth one. So okay, yeah, this is F1 hat of t, F2 hat of t, F3 hat of t, and F4 hat of t. 1, 2, 3, 3, 1, 2, 3, and 1, 2, 3. Okay, so the first basis that we had obtained was this. So this is 1 by root 3. The second basis that we had obtained was something like this. So it was under root of 2 by 3 here, and it was minus 1 by root 6 here. The third basis that we had obtained was this. It was all 0. And the fourth basis that we have obtained is 0 here. Then it takes the value 1 by root 2, and then it goes minus 1 by root 2. So this is 1 by root 2, and this is minus 1 by root 2. Okay, these are the basis, orthonormal basis, which we have obtained. Effectively, this, and this, these three form the basis for, or to be more specific, these three form the orthonormal basis of signals S1T, S2T, S3T, and S4T. Any questions? So this was the last question that I had planned to cover today. If you have any questions, please feel free to ask, and if you don't have any questions, you are free to leave the meeting. Thank you for attending today's session. Hope to see you all in the coming sessions. Thank you.